Okay, so we're going to wrap up linear momentum here. We didn't quite get through it all in class on Wednesday. Now here's an example. This is a really neat example because it's going to pull together a couple of these conservation laws that we talked about together into one problem. And it goes to show you the power of this when you start to put it together. As I've talked to you before about one of the things that excited me personally about physics was its ability to predict the future. Putting things, measuring, knowing some masses and where they are at the moment and how they're moving. I love the ability to use equations and mathematics to crank through and predict what would happen if I let the thing go and let the system run and let nature do what it would do and being able to predict it. So here's an example of that. It says we have two metal spheres. They're suspended by vertical cords, okay, and they're initially just touching. So the initial setup there is towards the middle of the screen, as you can see right in this area right here, okay. The two are hanging side by side, ball one and ball two hanging from strings side by side like that initially. Okay, it says sphere one with mass 30 grams is pulled to the left to a height of 8 centimeters. Okay, so this height here, 8 centimeters. Okay, and then it's released from rest. And so it says after swinging down, it undergoes an elastic collision. An elastic collision. Does it say perfectly elastic? No, but guess what? We're going to model it as perfectly elastic. Okay. The idea is that when you solve these kind of problems, if it says inelastic collision, you assume it's perfectly elastic. If it says inelastic, you assume it's perfectly inelastic, unless it specifies otherwise, unless it gives you additional information that would allow you to determine how much energy was lost and so forth. If it says elastic here, though, we're going to assume perfectly elastic, which means the kinetic energy is going to be conserved. Okay? And so they say after swinging down, it undergoes an elastic collision with sphere 2, whose mass is 75 grams. What is the velocity V1 final of sphere 1 just after the collision? So after this ball is released and it comes down and hits into ball 2 obviously is going to get pushed to the right as shown, but they want to know what's the speed of ball 1 then after that collision happens. Okay, so that's the setup for the problem. Okay, so as we take a look at this, we have our diagram to the left, and notice I did use a dotted box to define the system, and notice again that I put the Earth inside the system here, and that's so that we can count energy. We don't have to worry about the force of gravity crossing over and doing work on the system. The force between the objects and the Earth, that gravitational force, will be accounted for in our gravitational energy. Okay, and so this problem actually has two parts to it. Okay, we've got the first part of the problem where the ball number 1 is released from rest from height h1, and it falls through that distance and ends up moving at a certain speed then that it's going to have before it collides with ball 2. And then we have part 2, which is what happens after the collision. Okay, the assumption here obviously is that ball 2 gets pushed to the right. The question is, what happens with ball 1? Does it continue to move to the right? Does it bounce backwards? And if so, not only which direction does it go, but how fast? And so as we go ahead and work this out, we realize there is this kind of well-defined point here where the problem is kind of divided, okay, between the before and the after. And so if we look at this problem at the beginning for part 1 of the problem, we know from the law of conservation of energy that the energy can't be created, it can't be destroyed, it can only change forms. So where's all the energy to beginning? Well, again, if we call the very lowest point here that the ball gets to, if we call that our 0 height, okay, maybe I should write that a little neater if I can. It's kind of small on the screen. There we go. That's my best attempt. So y equals 0 will be down here at the height ball 1 is after it swings down to its lowest point. Okay. If I call that the 0 level, then obviously the ball is starting at a height above the 0 level, right? So it's going to have some gravitational energy, but it's not moving when it's released. And so all the energy initially is gravitational. There's no springs in this problem. No mention of friction, no winds coming from outside our system going through the system, nothing of that sort. So all the energy is initially gravitational energy. Once ball 1 gets down to the bottom, down to this point, it's down at the zero height, which means there's no more gravitational energy. All the energy is going to be in the form of kinetic energy. So we know the initial gravitational energy the ball has to be equal to its final kinetic energy. And we've seen this kind of calculation before. It ends up that the speed of the ball 1 at the bottom of its arc there is the square root of 2gh, where h is the height it fell through. And we go ahead and calculate that, and we get a speed for the ball number 1 before the collision, right? This is its speed before it hits ball 2, a 1.252 meters per second. Now that we know that, and knowing the mass of the two balls, they had told us that, the one was 30 grams, the other one was 75 grams, we know that our we're going to have a collision that happens here that's elastic. Now, when we look at the problem, there is a bit of kind of a curve going on here, right? However, if we kind of zoom in, if you could imagine, zooming in on just the collision process here, it can be approximated as a straight line collision, a linear collision. Okay, in other words, the balls don't start curving very much until they're some distance away from that collision process. So during the collision, it's a head-on, perfectly elastic collision, and we know that we have special equations that we derived in our last lecture that will work for this. And since we're interested in the final velocity of ball 1 here, we pulled out the equation that solves for v1 final. If we're careful putting the values in here for m1, m2, v initial 1, or v1 initial and v2 initial, we should be able to get the right answer. So again, if we want to do things in standard units and get our answers in meters per second, it's usually a good idea to do everything in standard units throughout the problem. Here it won't really matter because we have the same units on the top and the bottom of this fraction. So this whole fraction here and here, these will be unitless fractions. So it turns out that even if, as long as we're consistent, we could have done this in grams. We could have had 30 grams minus 75 over 30 plus 75, and we would get the same ratio. Okay, but being kind of disciplined, or being, in our problem-solving process, the strategy is usually to be sure you're not making a unit mistake. Just use standard units if you want to get standard units. And so that's what I did here. I said, well, 30 grams is 0.030 kilograms. We subtract off mass 2, which was the 75 gram ball, which is 0.075 kilograms. Divide by the sum of the masses times the initial velocity of ball 1. That's the velocity of ball 1, remember, when it gets down here to the bottom and when it's going to be colliding into ball 2. So that's my initial velocity of ball 1 in this collision process. Over here on this side, I get 2m2 over m1 plus m2, right? And then I put in the initial velocity of ball number 2. Ball number 2 is sitting here at rest waiting to be hit, so it has no velocity. So this whole term, in this case, drops out. We crank through the calculation and we find that the final velocity of ball 1 after the collision is actually negative 0.537 meters per second. So ball number 1 comes down and it bounces back and pushes ball 2 to the right. Okay, and so we not only get the this direction of the motion of ball 1 with our sign, but we also figure out how fast it's moving. And again, all without kinematic equations, all without using vectors and F equals ma. So there's a very powerful problem. We could predict what was going to happen in that situation by using just conservation of energy and conservation of momentum. Now, another important thing to be aware of is sometimes we have more than two objects involved in a system, right? Sometimes we have a rocket that's interacting and it's one object that kind of becomes two, right? The rocket shoots out exhaust gases and then the exhaust gases push back on the rocket. And so a lot of these problems that we've been looking at here have two objects involved in the collision process. Our lab this week dealt with kind of a transfer of momentum through a stationary object to a third object. Well, what do we do if we have a whole collection of objects, like a lot of little objects? Well, imagine if you had a collection of a whole bunch of little masses, and all together you might put a big dotted box around the system and say, well, what's the momentum of the system? And you might add up the mass of all the little objects in the system and say, well, that's the total mass of the system, and then multiply by the overall velocity of the center of mass, the average position of the mass of that system, and you would say, there's the momentum of my system of particles. Okay? But what if you did the calculation by taking each individual mass, each individual particle times its individual velocity? In other words, what if we got the momentum of each individual little particle and just started adding those together? Well, it turns out that if you were to sum up all those momentum vectors, can you imagine? Could you imagine, you'd be like taking all kind of vectors and stacking them, these different, maybe the molecule's going really fast that way, this way. You add them all together, all the momentum vectors, and what you're going to find is that you're going to end up with an answer that's equivalent to taking the entire mass of the entire system, right? Where this is the M1, M2, M3, M4, all of those added together, the entire mass of the system, right? Times the velocity of the center of mass. So it's remarkable that it works out that way, but it does, and it's quite a convenient thing to know, because it takes some problems and helps us, actually we can get a very simple answer to an actually very complicated question, and I'll show you that in just a second. Before showing you that, notice that if we differentiate, if we take the derivative of the left side and the right side of this equation with respect to t, if the masses are constant, then what happens is dv dt on the left turns into the acceleration of the center mass, and then the acceleration of each of the individual little particles in the system. And we end up with a fairly similar sort of a rule here, which is that if we add up the net force, if we add up all the force vectors acting on all those little particles, we get the mass of the large object times its acceleration. So this is why when we looked at a system and we applied F equals ma, we applied that rule, net force equals mass times acceleration. If you remember, we said we could apply that to a system, and we defined our system. The reason that worked is because of exactly this, the fact that this, this overall force on all the little particles added together, all those force vectors, is going to be equal to the total mass of the system times the acceleration of the center mass. So we see some nice connection between the rules that we've learned on a microscopic level, where we're dealing with each little individual thing, compared to what we see at the macroscopic level when we look at the whole system all at once. Okay, we see nice connection between these things. And so a simple example of that is to think about the air in the room in which you're now sitting. And the chance is that the total momentum of the air in the room is 0, okay? Unless there's a breeze in your room right now, which I'm going to assume there's not, right? If you're sitting in a closed room inside your home right now, then unless there's a breeze, then the overall mass of the air in the room times its overall velocity of the center mass of the air in your room right now should lie somewhere towards the center of the room, probably. And it's not moving, right? The air is not moving through your room, and therefore the total momentum of the air in your room is 0. Now, interestingly enough, the air is made up of all kind of little particles, molecules, I should say, of air, right? Some nitrogen N2 molecules, some O2 molecules, some argon molecules, some carbon dioxide molecules, and so on and so forth. And so these are moving around in the room around you right now very, very quickly, and they're making collisions off of each other at hundreds of meters per second. They're moving very quickly. They're very tiny. You can't see them, but they're constantly banging into each other and exchanging momentum, and their speeds are changing, their velocities are changing all the time, kind of like in that diagram at the bottom. So if we were to take each of the individual air molecules in your room right now, which would literally be, I don't know, trillions, quadrillions. I don't even know how many air molecules would be in the room that you're in right now. You'd have to calculate it. At standard atmospheric pressure, though, it's huge. Okay, so you have a tremendous number of air molecules, and if I knew the velocity, if I had the computational ability to get the velocity of each and every one of those air molecules in your room right now, at that instant, some instant in time, and I summed up the momentum vectors of all those air molecules. Could you imagine doing that calculation? It's hypothetically possible, but actually, we don't have the computational ability or the measuring ability to actually even do this. But what we do know is that if we add up all those momentum vectors for all those individual little air molecules in the room, guess what? They would add up to 0. Okay, they would sum up to 0. those little momentum vectors, as we connect the chain together of however the chain goes, remember we talked about adding vectors graphically, they close on themselves. Okay? They would add up and come back to 0 because the mass of the air in your room right now is not 0, but we know that the overall motion of the center of mass in your system is 0. There's no breeze in your room right now. The air molecules all kind of balance out in the directions they're going, okay, which is why you don't feel wind right now in the room you're in. And so while we can't do this calculation, right, I mean, it would be impossible to do that calculation, yet we still know the answer. We know the answer is a 0 in this case, okay, because we know the answer to this simpler question. So does that make sense? So that's an important idea. Sometimes a problem is too complicated to solve, but there's another problem that's equivalent, if you will, where that we know the answer of a simpler problem related to it that allows us to know the answer to the question that we couldn't actually do. Okay, I hope that makes sense. Okay, so at this point we'll do an in-class exercise, and again, this is not one you have to submit, but you may want to pause the video, read it, and give it a try, and then resume the video to see how you did on the question, just a way of breaking up the lecture today. So if you want to pause the video at this time, you may. Okay, so how did you do? The right answer here was that the direction of the velocity of the center mass of the system would be 1/4 the speed v and moving to the left. How did we get that? Well, it says consider a system of two particles. Ball A with a mass m is moving to the right at speed 2v. So here's our ball A with mass m moving to the right with a speed of 2v. Okay, and ball B has a mass of 3m and it's moving to the left at speed v. So whoops, make that a little bit bigger. So here we have a ball that's a little more massive, 3m, and it's moving to the left at speed v. Okay, if the time interval before the two balls collide, what is the magnitude and the direction of the velocity of the center of mass of the system? So if you're thinking back to the equation for center of mass, you're thinking, well, geez, I got to do m1 times x1 plus m2 times x2 and then divide by the total mass of the system. And I'm going to get a mass, it's a position that's closer to the mass that's larger, right? So maybe the center mass of the system's over here somewhere, okay? But these things are moving. They're moving, and so that center mass is going to move. And so when you first start thinking about this, you think, wow, how do I figure that out? Well, we use the fact that we just learned on the previous page. We use the fact that the answer to this question, while it would be difficult to solve try to figure out how the center of mass would be moving if we tried to use the center mass formula. What we can do is we know that the mass of the system times the velocity of the center of mass of the system is equal to each individual mass times its velocity added up. And so what I can do is use this rule to solve for this thing, which may have been difficult if I were to try to go right to a center of mass calculation. So anyway, what's the total mass in the system? The total mass in the system here is 4m. We have a mass m, and we have a 3m. And so that times the velocity of the center of mass has to be equal to mass 1, which is m, times its velocity, which is 2v, plus the mass of object 2, which is 3m, times its velocity, which is negative v. Remember, signs matter. These are vectors, right? And so when we go ahead and do the math here, what do we get? Notice every term has an m in it, actually. All right? So it turns out that the mass m doesn't even matter. It's just the fact that this object is 3 times larger, or 3 times more massive than the first one, that makes a difference. And so what we end up with is that the velocity of the center of mass, okay, is going to be equal to 2v minus 3v divided by 4, which ends up being minus v over 4, which means that the velocity is to the left, since we called our original velocity here to the right positive, and we labeled this one negative for going to the left. Because that's the case, then the negative sign indicates that it's moving to the left. Our center of mass would be moving to the left, and it would be moving at a velocity of 1/4 the velocity of ball, or 1/4 of the velocity v, where v is the speed that was indicated in the problem. So hopefully that makes sense. That was just an application of the previous slide, what we were talking about on the previous slide. So this takes us to our challenging question for the day, which is our in-class exercise that I do want you to submit your answers for. Okay, so this is a bit of a challenging question, but it's also important to practice. And so when you get your answer to this in-class exercise question, you want to log into Canvas and go to the quizzes and select the two-dimensional in-class exercise question quiz and submit your answers there, and that will go into our gradebook as an in-class exercise. So while this does count for credit, it's nothing to get too worked up about, because we have a lot of these in-class exercises, so it's actually a very small part of your course grade, but it's still, it's an opportunity for some of you looking to improve your grade to gain a little bit of ground. So as we look at this particular problem, we have this red ball, and it's moving at an angle of 50 degrees off the y-axis, and we have this blue ball that's moving horizontally. They give us the initial velocity and mass of each of these balls, which means we know what? We know the initial momentum in the system before the collision. Okay? Now remember that typically what we've been doing is one-dimensional collision problems, but in our lab we started to talk about two-dimensional collisions and this week. And so here, if you remember what we learned in the lab, you apply the law of conservation of momentum along each dimension, right? So the initial momentum in the x direction in the system is equal to the final momentum in the system in the x direction, right? And the initial momentum in the y direction, right, in the system is equal to the final momentum in the y direction. Okay, in other words, momentum is conserved in a system along each dimension. And so basically what we need to do is get the momentum vector of this in x and y components. We need to get the momentum vector of the blue ball in x and y components. And then what we know is adding up the x components of these two momentum gives me the initial x momentum in the system. Okay, and then we know the final momentum in the x direction at the end between these two has to be the same. And same with the y. So we're conserving momentum along each dimension. Okay, so after the collision, they tell us that this ball moves off at a 35-degree angle at this speed. And what they want us to figure out is how fast does the red ball move after the collision, and at what angle here, theta, does it move off. So you're looking to solve for V final for ball 1, the red ball, and you also want to know what angle it launches at. Okay. Furthermore, and so that's part A, and then furthermore in part B of the question, it wants to know, was the collision perfectly elastic? And the question is, was it perfectly elastic to within 5%? That is the final kinetic energy in the system approximately the same as the initial kinetic energy in the system? Let's say within plus or minus roughly 5%. Okay, if it's within about 5%, we'll say that's a perfectly elastic collision. Okay, it's hard to get a perfectly elastic collision in life, so we'll consider this perfectly elastic if our answer between the final kinetic energy compared to the initial kinetic energy is off by about 5% or less. We'll consider that perfectly elastic. So do this problem, and then when you're ready, log into Canvas and enter your answers. Okay. Now, one more interesting problem to look at before we call it a day here, and that is the rocket problem. Okay, I think just almost all the questions we've been dealing with in the course, we're dealing with objects that don't change mass, right? But on occasion, there are objects that change mass, and they change mass dramatically enough, quickly enough, that we have to use kind of some different rules, or we have to account for that. And so, a rocket is an example of that, because a rocket, especially when it's launched from planet Earth, you may not know this, some of you, but about 90% of the mass of the rocket initially is fuel. And so when a rocket is launched, like rockets launched into orbit, about 90% of the mass, when it's sitting on the launch pad, 90% of that mass is fuel. And so as the rocket launches up through the sky and into the atmosphere, above the atmosphere, that fuel was burned and shot out the back. And so the rocket that actually gets up to high altitudes is much smaller in mass than what was launched. So this burning, and it only takes a couple minutes for the rocket to be from the ground up into orbit. And so this is a very, very quick process, and the mass of the rocket's changing dramatically. So when we go to solve this conservation of momentum problem, it's not quite as simple as we were making it out before, in that, okay, A puts a force on B, B puts an equal and opposite force on A, and blah, 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 we just conserve momentum. It turns out this is happening so quickly that the mass of this rocket's changing such that the answer for the velocity we get, the answer we get for the forward momentum of the rocket and its speed changes pretty quickly. So the way we have to do this is we have to use some calculus and set this problem up in an interesting way. So we'll call the amount of mass of exhaust gases that's shooting out the back of the rocket, we'll call that amount dm. That's the small change in mass over a short period of time of the rocket fuel coming out the back of the rocket. Obviously, then that will take the original mass of the rocket, and we will be subtracting off that fuel that shoots out of the rocket, and that will be the mass of the rocket. Okay, that little bit of rocket fuel shooting out the back, of course, will increase the speed of the rocket from v by some small amount we'll call dv. And then it turns out in the reference frame of the rocket that if this is the speed of the rocket, then v exhaust would be the speed of the exhaust gases coming out the back of the rocket. Okay, so we're going to use Vex for V exhaust for the speed of the fuel coming out the back of the rocket. So when we go ahead and look at this, I'm sorry, it's the exhaust velocity. Excuse me. Yeah, right. Because yeah, it's going to be in the negative direction. So V here is an exhaust velocity, not the speed, because they're not adding together there. The velocity of the exhaust is the opposite direction. So V sub Ex is the velocity of the rocket gases shooting out the back relative to the rocket. Okay, that's important, relative to the rocket. All right, so when we go to solve this, we know that momentum has to be conserved. If we put a big dotted box around our system here, right, and when the rocket shoots its gases, there's no change in momentum in the system. There's nothing that came across our boundary that's interacting. It's an interaction that's happening inside our dotted box, so linear momentum must be conserved. So what do I have for the initial momentum in the system over here in the first picture? So this is kind of like the beginning, and then here's like later on, it's over here at this situation, right? So position 1, or the beginning here, we've got a mass of rocket and fuel together of m, and the speed of the rocket is v. So maybe it's already drifting along in space. So that's the velocity of the rocket, excuse me. So what is the final momentum after the rocket fires its gases? Well, here we have our dm, and then that has to be multiplied times the velocity of the exhaust gases, which again, relative to the new velocity of the rocket, we would be simply adding on that exhaust velocity Vx. And so there's the velocity of the exhaust gases. And then we have the new mass of the rocket, having lost this little bit of fuel over here, times its new velocity. And so there would be my final momentum, or my momentum at position 2. So the momentum at position 1 has to maintain and stay the same as the momentum at position 2. Now, interestingly, when I go to do the math on this, and I distribute through, multiplying, right, each term here, right? So I'm going to kind of do my math here, right? You know how to do this. When I do the math out, I end up with an equation here. mv equals v exhaust dm plus vdm plus dm dv plus mv plus mdv minus vdm minus dm dv. Now, again, dm dv is the same thing as dv dm, just opposite, So in other words, if it's the same two terms multiplied together, we know that that's multiplication is commutative. We can flip-flop, m times dv is the same as dv times m, so on and so forth. So when I look at this, I've got a vdm here, and I've got a negative vdm here. So those two sum together to give me 0, right? I have a plus dm dv here, and I have a minus dm dv here. So those two add together to give me 0. And then I've got an mv on this side, which if I subtract mv off of this side, I can subtract mv off of this side. And what I'm left with is a fairly simple equation that 0, remember if we subtracted this, this goes to 0 if we subtracted this term, right? what I get on the left is a 0, and on the right I just have Vx, exhaust gas velocity, times with respect to the rocket, times dm plus m dv. And so this equation must be, this equation here must be my equation that's true. Okay? Now, if we take that equation and we divide by capital M, the mass of the rocket, we get the following equation. And you might recognize that to get from dv here, to get from dv to v, we're going to have to integrate, right? Because when you take when you differentiate, you're doing the opposite of integrating. So if we want to get back to what v would be, we have to integrate. So if we integrate dv from v initial to v final over on the left side, then we have to integrate on the right side as well, and we're going to integrate from the initial velocity or initial mass of the rocket to the final mass of the rocket. Okay, as this process continues, the exhaust velocity of the gases is not going to change throughout the problem. We're going to assume that the gas is being shot out the back of the rocket with the same relative speed compared to the rocket. In other words, if the rocket is normally shooting out the gases at 200 miles per hour from the back of the rocket, it's going to continue to do that. So we end up with this equation. And of course, when we integrate dv, we just get v, and so we then evaluate it from v final minus v initial, so we get this on the left side. Okay, over on the right side, we get the minus v exhaust, and then when we integrate dm over m, we end up with the natural log of m final over m initial. If you remember your rules for logs, if you flip-flop this fraction, if you would make that m initial over m final, you can get rid of this minus sign. In other words, you can use the exponent rule for logarithms. And so what we end up with here is that v final minus v initial, so v final equals v initial plus the exhaust velocity with respect to the rocket times the natural log of the initial mass of the rocket divided by its final mass. Okay? And so that equation right there can be very, very handy. If the initial velocity of the rocket were 0, it's even simpler, but that's not always the case. The rocket may be drifting along in outer space when it fires its rockets. Okay, so v initial plus, I'm sorry, that's a plus there, yeah. Okay, so really nice equation, and I'll show you now how we use that. Okay, so here's an example that we want to solve using that equation we just derived, and let's take a look and see what we've got here. It says we have a rocket in space. It has an initial mass of 100,000 kilograms. Assume 50% of this mass is fuel. The rocket then fires its engines, which shoot the exhaust gases out at 200 meters per second. The rocket was initially moving at 25 meters per second, and the engines fire continuously until the rocket has consumed a half of its remaining fuel. How fast does the rocket end up moving? Okay, so let's think about this. We've got a rocket, and it's initially moving at 25 meters per second, so V initial is 25 meters per second. We'll assume it's moving to the right. And half of that mass is fuel. Okay, so that means the rocket mass, the mass of the rocket plus the mass of the fuel, the mass of the rocket therefore must be 50,000 kilograms, and then the mass of the fuel must be 50,000 kilograms. Okay, if you're following along in my explanation here. Okay, so the rocket engine fires, right? The engines fire and shoot exhaust gas out the back. And the rate at which they exhaust the gas, we were told, is 200 meters per second. And so we know the exhaust gas speed, we know the initial speed of the rocket, and we know the total mass initially, right, of the rocket initially was 100,000 kilograms. But at the end of this process, it's lost half the fuel. So if half the fuel is gone, that would be 25,000 kilograms of the fuel. And so that means after the rocket has launched its rocket engines here, okay, sometime later, the rocket now has much less fuel in it, doesn't have as much fuel in it, but now it's moving at some final velocity which we want to determine, okay, where it shot the rocket exhaust out the back like that. Okay, and the mass of the fuel that's remaining here would only be 25,000 kilograms, but then we also have the mass of the rocket, which is 50,000 kilograms. So the final mass of the rocket here, after launching, sending out the fuel, would be 75,000 kilograms. Okay, so now we take our equation, and the equation that we had derived said that the final velocity of the rocket is going to be equal to its initial velocity plus the velocity of the exhaust gases times the natural log of m initial over m final. Okay, and so in this particular case, that's going to be 25 plus 200 meters per second for the exhaust gas times the natural log of 100,000 over 75,000. And here's where we pick up our handy dandy calculator. And you can try this at home if you would like while I'm doing it. 100,000 divided by 75,000. Okay, and then we take the natural log of that, natural log, and I multiply that by 200. And now I add that on to my 25 meters per second, and you can double check me, but I'm getting an answer of about 82.5 meters per second. So the rocket will be moving at a much higher rate of speed after this process. Now, interestingly enough, on the other hand, if we were to take that equation that we had a couple slides ago, right? We were deriving our rocket equation. What if we were to divide both sides of that? Instead of doing the integration like we did before, what if we were to divide both sides by dt and then multiply both sides by m? Okay, so in other words, I'm going to divide both sides by dt, right? And then multiply both sides by m. And so when I do that, what I end up with is m dv dt equals negative v exhaust times dm dt. Okay, this equation is pretty handy. Okay, we can make it a little simpler here by recognizing that dv dt is the acceleration, right? dv dt, the time rate of change of the velocity, is the acceleration of the rocket. And dm dt here is the rate at which the fuel is being exhausted. Now, it actually is a negative number if you think about it. The rate at which we're, well, dm dt is the rate in units of kilograms per second that we're burning fuel, right? Our standard units for mass is kilograms, standard unit for time is seconds. So the rate at which we're burning fuel in kilograms per second is what dm dt is. And again, compared, you either look at it as the space is gaining an amount of mass, dm dt, or the rocket is losing an amount of mass, dm dt, but at a rate r, dm dt. And so we're going to call that rate r, right? We're just going to simplify the equation a little bit by saying, okay, well that rate at which we're losing mass out of the back of the rocket as exhaust gases, we'll call r. And so if I go ahead and substitute that in, we get this nice little equation here that the mass of the rocket times its acceleration equals the rate at which it's burning fuel in kilograms per second times the velocity of the speed of the exhaust gases. Obviously, the exhaust gases are going to push the rocket forward. And so if we solve that for the acceleration of the rocket now is a fairly simple thing to figure out. You just figure out the rate in kilograms per second that you're burning fuel times the speed of the exhaust gases divided by the total mass of the rocket, and that's going to give us our acceleration of our rocket. So let's take a quick look at an example of that. Okay, so let's take a look at an example here of using that equation we just derived. It says here that a rocket whose initial mass is 850 kilograms is in deep space and consumes fuel at a rate of r equal to 2.3 kilograms per second. The speed of the exhaust gases relative to the rocket engine is 2,800 meters per second. Notice everything here is in standard units. Okay, our values are all in standard units. This m, or this mass, 850 kilograms, would be the mass of the rocket, and of course this would be, in our equation, is the V exhaust. Okay, they want to know what rate will the rocket accelerate and what is the thrust of the engines. Well, if we take the equation we just derived and we go ahead and plug these things in, R was 2.3 kilograms per second. The exhaust gases, with respect to the rocket, they're shooting out the back of the rocket at 2,800 meters per second as measured by the astronaut, for example, and then we divide by the total mass of the rocket, we very quickly can calculate and find that the acceleration of the rocket is 7.576, and it would be in units of meters per second squared, standard units for acceleration then. Okay, so to then get the thrust of the rocket engines, all right, we would just use F equals ma, and we say, well, if we know the mass of the rocket now, we multiply that times the acceleration of the rocket, and it's the rocket engines that are pushing on it, then this is the thrust, the 6,440 newtons is the thrust of the rocket engines. That's how hard the rocket engines are pushing against this rocket, pushing it forward. Okay, so again, people say, you know, well, it's not rocket science. Well, this is rocket science. We're actually doing rocket science here, and it's kind of fun, and it's kind of interesting that we can do this, and it's really not that hard, is it? Okay, we're going to end there for today. Keep working hard. Remember, your homework number 10 is due by the end of the day on Monday by 11:59 p.m. on Monday evening, and I will get your next quiz up online. Have a great holiday weekend. Those of you that celebrate it, happy Easter, and take care. We'll see you soon.